Okay, so we're going to develop the growth function. It's a measure of complexity for a hypothesis set that's not as crude as the number of hypotheses it contains. The size, that's very crude. It tends to be overkill, doesn't capture diversity. Okay, so you can think of the growth function as an effective number of hypotheses. The sort of key insight, the key idea is to view a hypothesis set through the lens of a particular data set. Okay, because at the end of the day, we don't apply hypothesis sets in the abstract setting on the whole input space. We apply it to data. Okay. All right, so let me show you an example. Okay. And, let's be concrete in 2 dimensions, consider 3 data points. Okay. And let us consider a hypothesis similar to the credit approval hypothesis, let's say, and let me call this, H or H1. Okay. And, plus, minus, so I'll label this guy plus, and I'll label these 2 guys minus. Okay. And here I'm illustrating that a hypothesis, a classifier, for example, in 2 dimensions or any number of dimensions, it separates out your space into 2 regions. Okay, the plus region and the minus region. And so if you're given any set of points, okay, then it'll assign to some of those points -1 and to some of those points +1. And so that's what a classifier does. Okay. And now I want to mention that, okay, here let's label these points x1, x2, x3. Okay, these are just points. So this discussion has nothing to do whatsoever with the target function. It has nothing to do with the y values in a data set. Just think of these as 3 arbitrary points that I have picked. Okay, I'm just trying to analyze a hypothesis set. I've not brought in the data set that we get from machine learning. So these are just 3 abstract points that I picked. Okay, now on these 3 abstract points, we say that the hypothesis H1 implements the dichotomy. So let me label the points x1, x2, x3. Okay, so we say that the hypothesis H1 implements the dichotomy minus, plus, minus. So minus, plus, minus. Okay, and so this is called a dichotomy. Okay, why dichotomy? Because so this hypothesis dichotomizes the data set into 2 different sets, one which we have labeled, minus, and one which we have labeled plus. So 2 different subsets. Okay, and now let's make the leap to a hypothesis set. Okay, which is a whole bunch of different hypotheses. Okay, who knows how many? So you have hypothesis set H with maybe H1, H2, H3, H4, all the way up to maybe H400. I don't know. Okay, just an example. Okay. Now this second hypothesis is different. Okay, what does that mean? That means that, on the space, the regions it assigns plus and minus to are different. They may be very different or only slightly different. But, okay, whatever the difference between these 2 hypotheses, we can certainly, evaluate the hypothesis H2 on the same data set. Okay, and maybe we get minus, minus, minus. Okay, fine. That's a different dichotomy. No surprise, because it's a different hypothesis. Okay, and let's see what H3 says. Okay, H3 might say plus, 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 and H4 might say, minus, minus, plus, and so on. Okay, so the entire hypothesis set, when viewed through this collection of points x1, x2, x3, implements a set of dichotomies. Okay, now, sooner or later, maybe let's say H9 is sooner or later, for example, once we hit H9, one of these dichotomies is going to have to repeat. Okay, so for example, H9 might implement, minus, plus, minus again. Okay, now we look at this and say, oh, interesting. Okay, does that mean H9 is the same hypothesis as H1? No, it's a different hypothesis. It's just that on these 3 data points, these 2 hypotheses agree. And indeed, okay, it's an easy counting argument to see that there can be at most 8 different dichotomies that appear in this table. A dichotomy is a row. There can be at most 8 different rows. Now, why is that? Because you can classify x1 in 2 ways, okay, times the 2 ways that you can classify x2, times the 2 ways you can classify x3. So that there are only 8 different ways in which you can classify these 3 points. And, that doesn't matter whether you're classifying in some abstract setting or you're classifying using hypotheses. Okay, there are just 8 different dichotomies. Okay, so that's an important observation. There are just 8 different dichotomies that can appear in this table. Okay, now let's completely generalize this discussion and now talk about an arbitrary hypothesis set and an arbitrary set of endpoints x1 to xn. Okay, so now we can have an arbitrary hypothesis set H, and we can list its hypotheses. So H has hypotheses H1, H2, and so on. And now the fact that I'm listing it, don't get hung up on that fact. We don't require that the hypothesis set be finite. We don't require that it be countable. It's just, just listing examples of hypotheses here. And here I have n data points, x1, x2, x3, up to xn. Okay, so now I'm completely generalizing. And this is n data points, and they can be any number of dimensions. Okay, and once again, each of these hypotheses in my arbitrary hypothesis set, for this data set is going to assign a set of plus or minus ones. For example, minus, minus, plus, plus, whatever. Okay, so this is dichotomy 1. Okay, and maybe minus, 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 everything minus, dichotomy 2, and so on. Okay. Now, clearly, if my hypothesis set is infinite, I'm not going to be able to create this table. But one thing I know for sure is that only a finite number of different rows can appear in this table. In fact, I can give an explicit upper bound, 2 to the n. There can be at most 2 to the n different rows. Okay. So let us define the hypothesis set H restricted to the data points x1 to xn. So we're going to define the restriction of the hypothesis set H to the points x1, x2 up to xn. Okay. And this discussion basically captures what I'm about to define. Okay, so H of x1, x2, x3 up to xn is just the set of dichotomies that are implemented by hypotheses in H on the data set, on the set of points x1 to xn. So it's the dichotomy. So if I want to define it formally, it's the dichotomy is delta, such that delta is implemented by some hypothesis H in H. Okay. So we will use the label delta for a dichotomy. Okay. Okay. Now, important observation. Okay, so this is the restriction of H to a data set. So you can think of this as we are viewing the hypothesis set H through the lens of this set of points x1 to xn. Okay. And the hypothesis set H is arbitrary. It can be uncountably infinite, but we don't care. Okay. It still implies that this set of dichotomies is finite. And now you can start to see the value of viewing a hypothesis set through the lens of a set of points x1 to xn. What is that value? It has immediately taken, for example, an uncountably infinite hypothesis set and sort of condensed it down into the set of dichotomies that hypothesis set can implement on these points. Okay. It's saying that, you might have as complicated a hypothesis set as you want. I don't care. What I really care about is what can you do for me on these points. Okay. And if your hypothesis set is not only large but diverse, you'll be able to do all the 2 to the n dichotomies. Okay. If your hypothesis set is not diverse, it contains mostly the same functions, well, in that case, you might only be able to do 2 or 3. Okay. And so we can quantify the complexity, which includes the diversity of the hypothesis set. We can quantify the complexity of a hypothesis set with respect to this set of points by the size of the dichotomy set. Okay. So we can quantify we can quantify the complexity of H on x1 to xn using the size of H of x1, x2 up to xn. So the size of a hypothesis set still plays a role, okay? But it is the size of the number of the effective number of functions you can implement on a set. Okay? And since there are at most 2 to the n dichotomies on x1 to xn, this is at most 2 to the n. Okay? It turns out that when viewed through the eyes of a set of points, this complexity is, it turns out that this complexity is essentially what we need to replace the size of the hypothesis set that we were using for the finite hypothesis case. So effectively what's happening is that an infinite hypothesis set, okay, when viewed through the eyes of a data set, and we'll always in practice have a data set in mind, okay, so a hypothesis set, no matter how complex and how infinite, when viewed through the lens, when restricted to a set of points, becomes finite. In fact, we can even give an upper bound, okay, on the size. Okay. So I want to address 2 questions. Okay. Well, the first question is, well, this is all well and good. It's nice. You develop this cute way of viewing a hypothesis set through the lens of a data set. Okay. But we don't know the data set that we're going to get in practice. Okay. So, but we need to pick our hypothesis set before we see the data set. Okay. And so what x1 to xn should we use for computing this complexity of a hypothesis set? That's the first question. So question 1. Okay, and I'll list the questions. Question 1. What x1 to xn should we use to compute the complexity of a hypothesis set? To compute the complexity of a hypothesis set. Okay, why is this an important question? Because we have to pick our hypothesis set ahead of time and we don't know what data points are going to pop up. For example, we don't know the data and must fix H beforehand. Okay, so that's the first question. And then the second question is, yes, okay, so you've managed to, reduce the infinite complex hypothesis set to a finite set of dichotomies that are relevant for the set of points x1 to xn, but, and then we've managed to find a bound on that size of 2 to the n. Okay, so is that bound useful? Question 2. Is the bound, h of x1 to xn, so this complexity, that's equal to 2 to the n, is it useful? Okay, so, we're going to answer these 2 questions. Okay, so let me erase. Okay. So, no, let's answer both of these questions. Okay, we have a little bit of space here. Okay. So, question 1, very easy to answer. Yes, we don't know which data points you may need to evaluate the complexity of a hypothesis set on. But that's, we're computer scientists. We're familiar with this sort of, method of algorithm analysis. We build an algorithm, okay, and we don't know what input is coming. So what do? We analyze the algorithm in the worst case. Okay. And why not apply the same logic, the same philosophy here? We don't know what data set is coming, and we would like to, we would like to be equipped with a measure of complexity for my hypothesis set. So let's define not the complexity, not with respect to a specific x1 to xn, okay, but with respect to the worst possible x1 to xn. So we will define the complexity of H as the worst possible complexity, the worst possible size of the set of dichotomies when H is restricted to x1 to xn, where you can choose these x1 to xn adversarially. Okay, so we will use worst case analysis. Okay, and we will define, and that is going to be the, that is going to be the final definition of a complexity of a hypothesis set when viewed through a data set of size n. Okay, so we will define M sub H of n. Why? Because n plays a role. N is the number of points with respect to which we are defining the complexity. So M sub H of n is equal to the maximum possible complexity. It's the max over all possible choices of x1, x2, up to xn. It's the maximum of the complexity. Wow, worst case analysis. Let's prepare for the worst. Okay? So when we view a hypothesis set and we are asked, what is the complexity of this hypothesis set with respect to a data set of size n, we're going to consider all possible data sets of size n, okay, and look at how many dichotomies this hypothesis set can implement, okay, and then take the maximum. So in words, okay, this is equal to the maximum number of dichotomies that H can implement on any data set of size n. Okay, so I'll underline the important words. Maximum number of dichotomies that H can implement on any data set of size n. Okay. Now, this is called the growth function. Okay. And it is going to be our effective measure of complexity. So you can think of it as an effective number of hypotheses. Okay, and since this guy, since the hypothesis set when restricted to n data points can implement at most 2 to the n dichotomies no matter what the data set, this maximum is also at most 2 to the n. Okay, and now we might be thinking, if I have a complex hypothesis set with uncountably many hypotheses, then, since I'm allowed to choose this data set, odds are that this bound is realizable, right? Odds are that I'll be able to find a particular set of n points for which I can actually get 2 to the n dichotomies. Okay, so let's address the second question, which is, is this bound on the effective complexity of a hypothesis set going to be useful? So question 2. Okay. Is this bound going to be useful? Is this bound going to be useful? Okay. So let's see where we are going with this. Where we're going with this is we're trying to plug this bound. Okay, well, we're trying to plug this, effective complexity. We're trying to replace this brute force size of H complexity with this effective complexity. So let me show you the error bar, okay, where this size of the hypothesis set is relevant. So in the finite hypothesis case, the error bar was, the square root of 1 over 2n, the log natural log of twice the hypothesis set size divided by delta. Now, of course, when we do the full theory, it's not going to be this same error bar, but it has the same form, and our goal is to replace this size of h with this effective complexity m sub h of n. So let's imagine that, we were able to do this and without having to change any constants. It turns out we have to change constants and so on and so forth, but heuristically what I'd like to do is replace this guy, okay? I'd like to replace that guy with m sub h of n. Okay. And where now the n will actually be the data set size. Okay. It turns out that it's not going to be the data set size. It's going to be twice the data set size. But let's not worry about technicalities. Okay. And now let's evaluate this error bar when this effective complexity is 2 to the n. Okay. So let me put in here 2 to the n. Well, forget about the constants and stuff like that. The log of 2 to the n the n is going to come out of the log and it's going to cancel this n. And that n in the denominator here was absolutely instrumental in making this error bar shrink. Okay? And rein in the out of sample error, making it approximately equal to the in sample error. Okay, so on face value, this doesn't look useful at all. Okay. We can ask, what kind of effective complexity would be useful? So anything that's polynomial in n would be useful. So instead of 2 to the n, if I had anything that's polynomial in n, so let's say I put here n to the power d, whatever I want, d. Okay. Now when I take the log, I get d times log n. Okay, so I get d times log n over n. But that's beautiful. Log n over n crushed to 0 eventually. It's almost like 1 over n. Not quite like 1 over n, but almost like 1 over n. So, two conclusions. The 2 to the n, if I succeed in computing an error bar for the infinite hypothesis setting where I can replace the size of the hypothesis with this effective size, okay, 2 to the n as that effective size is not going to help me in getting that error bar small. Okay, it's going to be almost as bad as, infinite hypothesis set. Okay, but polynomial growth function will. Okay, so 2 to the n, this bound is of not much use. Okay, so we are going to have to address this issue and also address the issue of can we replace the size of the hypothesis set with this effective size. We're going to have to address both of those issues. Okay, and the first issue we're going to address is this 2 to the n. Okay, is all of this discussion, for naught? Because it will be for naught if, for all hypothesis sets that we are interested in, the effective complexity is 2 to the n. Okay, so let me erase the board. And what I want to do is I want to consider now some examples of infinite hypothesis sets, and let's just see if we can compute the growth functions to get a feeling for the growth function. Okay, and that'll give us some intuition for what's going on with growth functions. And then, I'm going to give you this combinatorial puzzle, and it'll look like out of the blue, but believe me, it's a very relevant combinatorial puzzle to the growth function. Okay, and that'll be the end of the lecture for today. Okay, so let's erase. Speed erase.